Hello, my name is Monica Ogrizek and I'm a PhD student at National Institute of Chemistry, Slovenia. I'm going to present a new laser ablation ICP-MS method for determination of metal content in PM deposited on quartz fiber filters. Particulate matter, or PM, are particles suspended in the air. PM are next to volatile organic compounds and greenhouse gases considered as air pollutants. They can originate from natural sources like sand, particles from volcano eruptions, or natural occurring wildfires, or from anthropogenic sources, for example from industry, traffic, or some combustion processes like heating of homes. And after PM is released in the air, it can hover there for a longer period of time and even get transported at long distances, as we know, for example, from Saharan dust events in Europe. But eventually, the PM are deposited to the Earth's surface, where we can breathe it, or it can have some toxic effect on vegetation or the environment. PM represents very diverse group of particles which depends on their source. They may contain inorganic compounds, as are crustal elements from the Earth's crust, ions, elemental carbon from the combustion processes, and trace elements. Organic compounds are mostly organic carbon. The size of PM is also dependent on its source, and it's from a few nanometers as soot to some micrometers as are pollen or Saharan dust. The PM10 is the label for particles smaller than 10 micrometers, and PM2.5 are particles smaller than 2.5 micrometers. So the number represents the cutoff size of the particle diameter. And why is PM so important? Because it has negative effect on many different levels and is considered one of the most dangerous air pollutants. It could affect the environment by disrupting solar radiation balance and consequently causes heating of the atmosphere. It can also influence the ecosystem. For example, it can be deposited on the vegetation surfaces or dissolved in the water and then change the nutrient balance or the availability of the elements. It could also influence the cultural heritage. For example, this black rust on the churches or some historic buildings is due to PM, and this can disturb and contribute to stone damaging processes. And last, it can have negative effect on health. The inhalation can cause pulmonary or cardiovascular diseases, which can be caused by particles itself or by some toxic components inside the particles, as are arsenium or cadmium. And fine particles with diameter smaller than 2.5 micrometers are more harmful because they can enter the bloodstream through the lungs and travel around the body. Therefore, PM and some components are already regulated in European directives, and also the monitoring conditions and standard methods are prescribed. So, PM is most commonly sampled by PM sampler. So we put in a blank filter. Here's an example for quartz fiber filter. And then the air is drawn through the sampling head, where we choose the size of the PM that we want, for example PM10 or PM2.5. And then particles get deposited on the filter, and the result is a loaded filter, where then many different analytes are normally measured, as they're listed here. And in Slovenia, the agency responsible for air monitoring is ARSO. This is Slovenian Environment Agency. And they monitor many different compounds, as are metals, Pah ions, elemental carbon, organic carbon. And they monitor it on the same sample, which is collected on daily basis. There are other filter metrics alternative, but quartz fiber filter is the only possible filter metrics for OCEC determination, and that's why we also choose to develop a method on quartz fiber filters. Um, and in the European Union, monitoring agency normally use the prescribed standard method, which is the 14902. And this method uses microwave digestion ICP-MS for its determination. In the European Union, there are some regulations and directives concerning air pollution. And here I would just like to point out the standard method for elements that I already mentioned before. This is 14902, and it is certified only for 4 elements listed here. But in the directives, the monitoring of some other elements are also required, as are, for example, chromium, selenium, zinc, and the standard method for those elements does not exist yet. And this is one of the problems that I would just like to point out. So this standard method for determination of lead, cadmium, arsenic and nickel in suspended PM prescribed sampling with PM sampler. Then a small subsample is taken from a sample and digested with the use of microwaves and concentrated acids. So the sample in a liquid form is obtained, and this sample is then analyzed by ICP-MS. The problem with this method is a microwave digestion pretreatment step, because it uses concentrated acids, which consequently ends up as toxic waste, and because it is standardized only for 4 elements. This is presumably because for other elements, digestion efficiency are not sufficient for all PM compositions, and it is also a time-consuming step. To avoid those problems, we developed a method with laser ablation ICP-MS, where instead of microwave digestion, we use laser ablation, which can use a solid sample and is directly coupled to ICP-MS. So how does laser ablation works? We put a sample in the ablation cell, and the laser head produces a laser beam, which ablates the sample, producing some aerosolized particles, which are then transported with argon or helium gas to the ICP-MS. So with laser ablation, instead of microwave digestion, we can use solid sample, so no pre-treatment step is needed, and consequently we don't have any toxic waste. We can have multi-element determination because we don't need to worry about the digestion efficiency, and we can also obtain lower LODs and require less sample for the analysis. And here I would just like to take you briefly through the method development steps. First, we did a parameter optimization, and we chose 3 parameters based on our educated guesses. The beam size, we chose the biggest beam size our laser ablation system is capable to produce, simply because if you're doing a bulk analysis on an area, it is faster if you use larger beam size. And then we optimize the fluence. This is simply the energy of the laser. And we tested fluence from 0.5 to 4. And we can see here that at fluence 0.5 the signal is a little lower because not all of the PM was ablated. So for the optimal parameter, we chose to be fluence 1.5 because above that fluence the signal stays the same. And another reason is that because at higher fluences some shredding of the filter occur, which could cause some problems in the instrument. And the next thing was the optimization of the dosage, and this is parameter is how many times the laser fires or ablates on the same area, on the same spot. And we can see here that with dosages, small dosages 1 to 3, uh, the not all the particles are ablated, uh, and from the dosage 10 above, the signal reaches a plateau. So above the dosage 10, the all the particles are ablated for the filter. That's why we chose 10 overlaps for sufficient dosage for ablating all the material. And we tried this on high loaded filter and low loaded filter. So the method would be robust enough for the winter samples where we expect higher concentration, and the summer samples when usually we have lower concentrations. The second thing we needed to assess was the blank filter, the filter without any PM deposited on, simply to see if the blank filter contributes to this measured signal. And the instrument has some background that is called gas blank. This is the background that is just from measuring gas flowing through the instrument without any ablation. And this is the green one. And then when we ablated the blank filter, this is the gray one, we compare those signals for every element to see if there is any difference. And as we can see here, mostly there is no difference between those signals, so there is no contribution from filter blank to the measured PM concentrations. In the next step, we wanted to determine a subsampling procedure, so we need to look into the homogeneity of the samples. And first we assess the influence of location on the filter to see if there is any difference in the position of elements between the edge or the center of the filter. So we ablated a few lines from the edge to the center, and as we can see here in the plotted signal, there was no trend observed in the ablation signal, and we concluded that there is no difference between sampling at the edge or in the center of the filter. However, we did find some strange spike randomly appearing through the measurement, which will be discussed in the later step. Next, we wanted to determine the smallest subsample size that would still be representative for the whole filter. First, we ablated a large area of the filter and find some large spikes which represent less than 1% of total number of pixels, but largely contribute to variability between the pixel, but does not drastically change the average of the samples. And because we wanted to know what is the average of the whole filter based on measuring only a small subsample, and in a small subsample the spike could have much larger weight than other pixels, we concluded that for this method it is necessary to remove spikes before the analysis. Here I would just like to show a representation of statistical analysis. So if this is our large ablated area, first we calculated the average of the whole area. This was a sample average. And then we divided the sample to units. And the value of every unit is the average of covering pixels. And then we took 3 random units, this was the subsample, and calculate its average and 95% confidence interval. And we repeat this for every possible triads and count how many triads contain the sample average in its 95% confidence interval. and if more than 95% of triads were appropriate, the size of the subsample was considered as sufficient. And we conducted the analysis on different unit sizes, on smaller and smaller. And here we can see the results for all measured elements. And we can see that with the decreasing of subsample size, the number of representative subsamples also decreases. And since we set the limit to 95%, the smallest representative subsample size was 3 randomly chosen units with 12 square millimeter size. The next step was the calibration of the results. The problem here was that laser ablation ICP-MS needs a matrix match standard for calibration, and that commercially available standard that would be PM on quartz fiber filters with certified elemental composition does not exist yet. Therefore, we used custom-made standard, and we took 3 real-life samples and measured its elemental composition by absolute method of INAA, Instrumental Nuclear Activation Analysis. And so we got the information on elemental composition. So we could use those samples as standard and quantify some other samples measured by laser ablation ICP-MS based on those results. As a final step, we compared the results from newly developed laser ablation ICP-MS method to absolute method INAA and standard method microwave digestion ICP-MS. Every triangle represents one element, and the 3 methods are placed one on each axis. The stars in the corners represent the statistically significant difference between the methods. Here we need to keep in mind that laser ablation ICP-MS and INAA are not totally independent, since laser ablation was calibrated based on INAA results. More interesting fact is that there is significant difference between microwave digestion ICP-MS standard method and laser ablation ICP-MS and INAA in 3 elements: arsenic, iron, and vanadium. And this result confirms that ICP-MS with microwave digestion could have questionable recovery rates because of this microwave digestion pretreatment, and that laser ablation ICP-MS is a better method for determination of the elements. And in the last slide, I would just like to summarize the presentation. And here on the right is the protocol for the developed method. And the method does not need any sample preparation, is more precise measurement and has lower LOD than standard method. It can determine more elements, uses less samples for the analysis, and does not produce any toxic waste during the analysis. And if anyone is more interested in the method, they can take a look at the recently published article in Talanta. And thank you for your attention.